Last time on SoME. Apparently you can't actually get negative real numbers into the domain. However, those values can be obtained as limits of values at nearby complex numbers with positive imaginary parts.
I see. Still a bit of a bummer that we did all that work for nothing.
Wait a minute. Will our question of the complex logarithm be next week's question? So,
You know, e to the pi I equals -1. Therefore, log of -1 should be pi I.
Yeah, that makes sense. Although, I think there might be a problem with that. But we'll get to that later.
Actually, I think I got an idea on how we can do this with all complex numbers.
Really? Let's hear it.
This is Euler's formula. It's a generalized form of Euler's identity. Let's say we want to find the logarithm of x plus iy. We can assume that the logarithm is a plus bi. We can break this apart into e to the a times e to the bi, and after that, we can replace the e to the bi with Euler's formula. Saying this equal to x plus iy, we can solve for a and b.
Good job, Sai. Let's take the point we chose for a in the last episode. If you remember, that's a half plus a half I. Plugging x and y into our formulae, b is equal to pi over 4 and a is just log of 1 over square root 2, which is about negative 0.3465735902a. Yes, the script actually contains that much precision. Plugging that into Wolfram Alpha, we do indeed get half plus a half I. There's a nice visualization of this. Here's the complex plane, and let's mark a point in complex space. E to the a corresponds to the distance from the origin to the point, while e to the ib corresponds to the angle between the ray to the point and the positive real line. And here we get to our second problem.
Our second problem? Oh right, an angle of pi over 4 is the same as an angle of 9 pi over 4, which is the same as -7 pi over 4.
Yes, so in short, there are actually infinitely many solutions to the equation e to the a plus bi equals x plus iy.
So I guess a complex logarithm is impossible?
Actually, no! Here's an example for real-valued functions. There are two solutions to the equation x squared equals t. However, in this case, we define the square root function as the positive solution. A similar idea exists for trigonometric equations.
Oh yeah, arc sine and arc cos. We restrict them so that those functions can only give values between pi and -pi. So I guess the complex logarithm is defined after all. Hang on, that's why we couldn't define the function properly for the negative real numbers. There's a discontinuity. Approaching from the top and the imaginary part is positive, and approaching from the bottom, the imaginary part is negative. However, I guess it's best if we define it as the positive solution for there.
So there we go. Shame that there's a discontinuity, but such is the way of the life. Even if a function is defined, it may not be continuous.
Wait a minute. What the heck?
Yes. This is what's known as a Riemann surface.
Wait, the same Riemann as the guy with the zeta function.
Yes. This is the second Riemann's hypothesis referenced this month.
He named a lot of stuff too.
Anyways, a Riemann surface is a way of deforming the complex plane, but this isn't your regular homeomorphic function. These guys have some structure. This spiral one specifically is called the Riemann surface of the complex logarithm. Oh, I forgot to mention, the complex logarithm is usually denoted like this. The capital L is important. First, we need a name for these points. Let's denote each point as r angle zeta, where r is the distance from the point to the origin, and zeta is the angle from the vector 1 angle 0, taking into account how many times it moves around.
So like the point 2 angle 4 pi is 2 units away and goes twice around the spiral.
Yes, the complex logarithm for a point on this surface is equal to ln of r plus I zeta. Remember, the complex logarithm can only map from this surface to the regular complex plane. There are some weird stuff going on here. For example, addition as we know it can't be defined here.
What do you mean?
If we want to add 1 and -1 on the regular complex plane, you get 0. Now, if you want to add 1 angle 0 and 1 angle pi, the answer should be 0, right?
Well, the angle can be anything, so we can call it 0.
However, 1 angle 0 and 1 angle -pi should still get the same result, 0. However, this means 1 angle 0 plus 1 angle pi equals 1 angle 0 plus 1 angle negative pi. So 1 angle pi equals 1 angle negative pi, which is true for regular complex numbers, but not here.
Yeah, in addition, you do remember what happens when you take the logarithm of 0. Complex or not, it's undefined.
However, while you can't do addition, multiplication acts as its addition. How do you multiply 2 points together? I'll give you a hint. R angle zeta is equivalent to RE to the I zeta.
Say we want to multiply R angle zeta and S angle phi. This is equivalent to RE to the I zeta times SE to the I phi. And remembering exponential rules, this is equal to RS e to the I zeta plus phi. So the answer is RS angle zeta plus phi. Hey look, when R and S is equal to 1, it seems like we're just adding the two together.
Ding dong! You're on the right track. Basically, the function from C to the Riemann surface e to the z is bijective, meaning it has a one-to-one correspondence, and you can turn any complex number into a corresponding Riemann surface point by exponential functioning it. And since the exponential of a sum is the product of their exponentials, addition in C maps to multiplication in the surface.
Wow, we did a lot today. And to think we got here because we want to extend domains.
Yeah.
Hey, did your classes start already?
Hey, it's not like this is getting in the way of my studies. Fine. Well, see you in SoME 11.